Hi everybody, this is the lecture on section 2.5, equations of lines and planes in three-dimensional space. Okay, so starting with lines, how does one define a line in 3D? Well, there's two ingredients that go into making a line in 2 dimensions. In 3 dimensions, it's very similar. What are the two ingredients that go into the equation of a line, the algebraic representation of a line in 2 dimensions, right? Either you need a point and you need a slope. So in 3 dimensions, what's the slope? I mean, we can no longer call it rise over run, but we can have a vector, right? So a vector will define a line in 3-dimensional space that goes through the tail point. Right, so you have this vector v is a slope vector. And then you have this base point p. So v is a slope vector and p is a base point. Okay, and let's give v some coordinates. We'll say p, comma, q, comma, r. And the base point p has got coordinates a, b, c. So now, if you want to look at any point on this line, say this point over here, right? If this vector right here is, well, what should we call that? Let's call that capital P, right? Capital P, this vector from 0, 0, 0 to the point A, B, C. And then this point over here, well, that's capital B plus some scalar multiple of V. And that's it right there. P, so what should we call that point? We'll call this point X is equal to P plus T times V, right? Some scalar multiple of V when added to P gives you any other point on that line. Positive scalars for T go for this half of the line, and negative scalars for T go towards this half of the line. Okay? So that's pretty simple. X is equal to P plus TV, right? So every point X equal to X, Y, Z on the line given by base point. I should make this black. Every point on the line given by base point P and slope vector V is, or satisfies, X, Y, Z equal to, well, let's call this X is equal to P plus T times V. So that's X, Y, Z is equal to, P was A, B, C, plus T times V is P, Q, R. So X, Y, Z is equal to A plus T, PT, B plus QT, C plus RT, like that. All right, so this is known as the vector equation of the line. Right, and then after that, well, we have x is equal to this, y is equal to this, and z is equal to that. So we have x is equal to a plus pt, y is equal to b plus qt, and z is equal to c plus rt, and this is the parametric equations of the line. Okay, so two different forms for the line, the parametric one and the vector equation of the line. And this also works in 2D, by the way. Well, first let's take an example of that, I guess. So, for example, the parametric equations for the line through point, let's say 1, 0, minus 2 with slope vector 3, minus 2, 2, like that. So the parametric equations of the line through this point with slope vector 3, negative 2, 2 are, well, write it down, x, y, z is equal to, put your base point here, right? Let's look at the equations up here. Here, the ABC is the base point, and the PQR, that's the coordinates for the slope vector. So it's base point plus slope vector times t in each coordinate. All right, so this is 1 plus 3t. 0 minus 2t. So just write minus 2t. And then minus 2 plus 2t. All right, and there they are. All right, well, what about the notion of parallel lines? So some notes. 1, 2 lines in 3D are parallel, right? Well, when their slope vectors are the same, or scalar multiples of each other. When their slope vectors say v1 and v2 are scalar multiples of each other. Right, so for example, x, y, z equal to, let's say, t, 1 minus t, 2 plus 3t, like that, and x, y, z equal to 9 minus t, 1 plus t, and minus 2 minus 3t. Maybe we'll make this a 2t, 6t. Our scalar are parallel because the slope vectors are as follows. So this one has got slope vector 1, negative 1, 3. You just read it right off the parametric equations. And this one has got slope vector, minus 2t, minus 2 plus 2 minus 6. Right? Just read it right off the parametric equations. Minus 2 plus 2 minus 6. But what is this? It's minus 2 times that vector. 1 minus 1, 3. Okay? So this one has got this slope vector, this one has got this slope vector, which is just minus 2 times that one. So the lines have to be parallel, same slope vector. But they're different lines because, you know, the base points are not on the same line. And you can check that. So two lines are in 3D are parallel when their slope vectors are scalar multiples of each other. And then non-parallel lines in 3D need not intersect. Right? I mean, you can have a line doing like this and then a line that sort of goes underneath it in 3 dimensions, but it doesn't have a parallel slope. Let's see, how can I do this? I don't think that's going to work. No. Okay, a little better. Right, the lines can just sort of pass over each other. Non-parallel lines in 3D need not intersect. And 3 parametric equations also work for lines in 2D. So in 2D, you have several ways of representing lines. Oops, wrong eraser. There's 3 ways now to represent lines in 2D. So let's take the line, say, that goes between points 0, 1 and 1, 3. Right? Well, what's the slope of this line? The ordinary slope. Well, it's 2 over 1, right? Rise 1, run 2. No, sorry. Rise 2, run 1. So this is y is equal to 2x plus 1. Right? So that's one way to represent the line. So that's the slope intercept form. Okay, but we've also got slope vector. Well, what's the slope vector? It's the vector that goes between these 2 points. So that's 1, 2. And base point would be, well, either 1, 3 or 0, 1. Which one should we pick? Well, let's do 1, 3. Doesn't matter which one you pick, you still get the same line. It's just not uniquely represented with parametric equations. Right, so we've got the vector equation. So that's going to be x, y is equal to base point 1, 3 plus t times slope vector 1, 2. Alright, so that's the vector equation. And then there's parametric equation, which is going to be x, y, 1, 3, t plus 2t. Alright, vector equation, and then these are parametric equations. Alright, so in 2D you can use the same idea to represent lines there, these parametric equations. Notice that x is a linear function of t and y is a linear function of t. And that gives you a line in parametric form, a line in the xy plane in parametric form. And we're going to use this idea later on in the course for sure. Okay. How about this? The distance of a point to a line. So suppose I've got this line right here, and we've got 3 points, right? Well, we got 2 points. We got this point P, and then I've got this point Q that's off the line over here. And I want to know what this distance here is, right? The perpendicular distance of Q to that line, and that's a right angle right there. And then the line has slope vector V. Well, if I take the vector here, PQ, like that, and then I've got this slope vector V. So I've got this base point on the line and the slope vector V defining that line, and then I've got this point Q off of the line. I now have this vector PQ. Okay, well, the area of the triangle made by PQ and V, I've got this angle theta here. Area of the triangle defined by PQ and vector V is, well, what is it? It's, well, actually I don't need to refer to that angle. As we talked about in the section on cross products, it's 1/2 the cross product of PQ with V, the length of the cross product. Right, but the area of the triangle is also the base of the triangle, which is V, times this height, which is this distance you're looking for. Right, but the area is also 1/2 base times the height, which is 1/2 the length of V times this D, that distance that you're looking for. Therefore, 1/2 length of V times D is equal to 1/2 times the length of the cross product PQ and V. So now I can cancel the halves and just solve for D. So that distance D is equal to PQ cross V over length of V. How about that? So that was a geometric problem in 2 dimensions that would have been done sometime in your pre-calculus class, perhaps. Right? You had a line, and then you had a point off of that line, and you wanted to find the distance of the point to the line. So what you had to do was find the equation of this perpendicular line that went through Q, calculate where the intersection point is, right? And then from that intersection point, calculate where the intersection point is. Oh, find the equation of the line perpendicular here, and then find the intersection point. So the intersection point is I, and then use the distance formula for I to Q, right? And then you would get that distance. But this is much easier. It's just a mechanical procedure: PQ cross V over the length of V, and that works in 2 dimensions as well. That works in 3 dimensions and in 2 dimensions. To make it work in 2 dimensions, you just add a 0 coordinate to, you add a 0 coordinate in for Z. Okay, you just do everything in the XY plane. So let's do an example of that. Example. So find the distance from the line to the point given. So let's say the line through 1, 1 and 3, negative 2, and then give me some point over here, 5, 0. All right, so I want this distance here, this perpendicular distance, which is going to be the shortest distance, right? Right, so calling this P, calling this Q, and then we have this vector PQ, right? So PQ is equal to, and remember to add in that third component. 5 minus 1 is 4, 0 minus 1 is negative 1, 0. Right, so PQ is 4, negative 1, 0. And then the V right here, right, V is going to be equal to 3 minus 1 is 2, minus 3, 0. Right, so it's a two-dimensional problem, but you can embed it in 3 dimensions just by looking at, this stuff for just x and y in the xy plane down here. All right, you've got that xy plane, and you can just embed it in 3 dimensions by putting in the z-axis and then letting everything happen down in here. All right, so here's this line. All right, there's your v and there's your pq. So you're just doing everything down in that plane there, and that's totally fine. It works out just fine. So you can bring the algebra of cross products, which happens in 3 dimensions, down to 2 dimensions in this way. So this distance d is equal to, well, let's do the cross product first. PQ cross V is equal, or not the length yet, let's just do the cross product. I, J, K, 4 minus 1, 0, 2 minus 3, 0, and something nice happens when you do the cross product of the 2-dimensional vectors inside 3D. The cross product for in the x coordinate, you just get 0, right? 0 minus 0. In the y coordinate, you just get 0 minus 0, so it's 0 again. It only just shows up in the z coordinate, in which case you get minus 12 plus 2 minus 10. All right, so now the length is easy to calculate. It's just 10. So the length of PQ cross V is just 10. And the length of V, well, is equal to, what do we got? 4 plus 9, so square root 13. All right, so the distance d is equal to the length of PQ cross V over the length of V, which is 10 over root 13. Okay? Alrighty. So that's lines in 3 dimensions. How about planes? Stop for a moment. Okay, planes in 3D. So in 3 dimensions, a 2-dimensional subspace in 3 dimensions is called a plane. So just to imagine a flat sheet, right, that extends infinitely in all directions. As with lines, there are 2 ingredients that goes into an equation for a plane. Okay, there's a point on the plane, P. Is a base point. And that's P. And then N is what's known as a normal vector, equal to PQR is a normal vector that is a vector perpendicular to the plane. Alright, so change the thickness on all that. Okay. Okay, so we've got a vector N perpendicular to the plane, and a point P that's a base point on the plane. Now, any other point, x, y, z, if you take the vector, I guess we'll call that point Q, Q equal to x, y, z. If you take the vector PQ, right, which is the vector from P to any other point on the plane, well, it's perpendicular to the normal vector. Okay, so PQ dot N is equal to 0. Right, so for any point x, y, z on the plane, okay, the vector PQ, which is equal to x, y, z minus the point P, which is ABC, dot N, which is PQR, well, those are perpendicular, so it's got to be 0. Right, so let's put down the vector form. Put down the vector form. So PQ dot N is equal to 0. So for any point Q equal to x, y, z on the plane, PQ dot N is equal to 0. PQ is, right, head minus tail dot N, which is this, is equal to 0. So what this turns out to be is x, y, z dot p, q, r equals a, b, c dot p, q, r. So we have px plus qy plus rz is equal to PA plus PB plus PC. And this is known as the Cartesian equation of the plane. All right, this is the Cartesian equation of the plane, and this is the vector equation of the plane. So let's take an example. Okay, remember that a line, be it in 2 dimensions or 3 dimensions, a line is defined uniquely by 2 points. Right? If you take 2 points and draw the straight line between them, that's the only line that contains the two. With a plane, that's defined by 3 points. Any 3 points on a plane determine it uniquely. Essentially, those 3 points will make a triangle, and then you just extend the triangle in all the different directions, and then that gives you the whole plane. So let's pick 3 points and calculate the plane that goes along with it. So find the Cartesian equation containing the 3 points let's say 1, 2, -1, and 0, 5, 4, and 3, -1, -1. Okay, so we've got these 3 points defining the plane. So we've got a base point. There's 2 ingredients that you need to define the plane. Okay, you need the base point, P, and the normal vector. Well, we have 3 choices for P, and any one of them will do. And now we need a vector that's perpendicular to the plane. Well, if you take those 3 points, you can make 2 vectors out of them like that. Right? Pick one point as the tail of 2 vectors, either this one, or this one, and then extend them. And that gives you two vectors. 3 different choices for 2 vectors, but it doesn't matter which 2 you pick. So 0 minus 1, -1, 5 minus 2 is 3, and 4 minus 1 is 5. And then this vector, 3 minus 1 is 2, minus 1 minus 2 minus 3, and -1 minus -1 is 0. So we'll call this vector u, and we'll call this vector v, and then a normal vector for the plane would be a vector that's perpendicular to both of these. Right? Well, what's the vector that's perpendicular to both of those? The cross product. Right, so we let in the cross product u cross v, which in this case is equal to I, j, k, -1, 3, 5, or I got them backwards, 3 minus 1 minus 2 minus 3, 0, and -1, 3, 5. So that cross product is, calculating it quickly, we've got is minus 15 for the x coordinate. For the y coordinate, we've got 10, minus 10. And for the z coordinate, we have 6 minus 3 is 3. Okay, so minus 15, minus 10, 3. And that's your normal vector. So now the equation of the plane right? So remember the vector equation of the plane. So usually we start with that. Let's go back up, take a look at it real quick. Right? PQ dot n is equal to 0. Right? But this boiled down to XYZ dot PQR equals ABC dot PQR. Right? So we can just write down this form. XYZ.PQR equals ABC.PQR. So XYZ dot PQR is the normal vector, minus 15, minus 10, 3 equals, now you can pick any one of the 3 points that you want for the base point on the plane. Right, I'll do 0, 5, 4, say. Dot minus 15, minus 10, 3. So I have minus 15x minus 10y plus 3z is equal to minus 50 plus 12. Right, so that is 38. So minus 15x minus 10y plus 3z is minus 38. And there it is. Okay, so notice, by the way, that in the equation of the plane, you can read off the normal vector. It's just the coefficients of x, y, and z, right? It's, in this case, minus 15, minus 10, 3, minus 15x, minus 10y, plus 3z. You can just read it right off the equation of that plane. And then, again, it didn't matter which of the 3 points that I used in calculating the dot product here. They all give the same answer. For example, like 3, negative 1, negative 1. Three minus 1 dot minus 15 minus 10 3. That is equal to minus 45 plus 10 minus 3. So that's minus 35 minus 3 minus 38. Same thing. Other point, 1, 2, negative 1 dot minus 15 minus 10, 3. So this is equal to minus 15 minus 20 minus 3, which is minus 38. Right? Same answer. It didn't matter which of the 3 that you chose. Just a couple notes about planes here. Two planes are parallel when what? When their normal vectors are scalar multiples of each other. Right? Two planes are parallel when their normal vectors are scalar multiples of each other. For example, so this one here, minus 15x minus 10y plus 3z equals minus 38, right, is parallel to, well, has n equal to minus 15 minus 10, 3. right? And then, I don't know, we'll say 30x plus 20y minus 6z equals 0 has n equal to 30, 20 minus 6, right? Which is 2 times this vector here, or minus 2 times that vector there. Right, so they're parallel. Okay, here's a note about drawing planes. How long have we gone here? Okay, 40 minutes, it's okay. A note about drawing planes. Any plane which does not contain the origin zero, 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 right, has an equation px plus qy plus rz equals d, right, for d not equal to 0. When it contains the origin, d will be equal to 0. When PQ, well, the x-intercept of the plane, right, since it doesn't contain the origin, the x-intercept, right, that's where y and z are equal to 0. Well, what's that going to be equal to? So that's equal to, well, if y and z is equal to 0, then x equals d over p. D over p, 0, 0. The y-intercept is d over q, 0. And the z-intercept is 0, 0, d over r. Right? So when you know the x, y, and z intercept, if you just connect those 3 points with a triangle, that'll give you, well, at least, some idea of a drawing of that plane on the x, y, and z coordinates. So this can often give a rudimentary idea of how the plane sits on the x, y, and z axes. Right, so without using actual numbers here, we can just draw it like this. So if this is x equals d over p, y is equal to d over q, and z was equal to d over r, like that. Well, I could just connect these 3 points with a triangle. And now that triangle defines the plane. All right, so it's not the best drawing of the plane in XYZ space, but it's often enough to help you solve some kinds of problems. Okay, so there it is. One last item is how to find the distance of a point to a plane. So I've got a plane. And therefore, I'm going to have and then I have a point Q that's not on the plane. And I want to find this distance here, D. Right? Well, since that's supposed to be a perpendicular distance, I also have the normal vector to the plane lying along that line there. Okay, now I don't necessarily know what this point is, but that's fine. So here's Q, and then I should know one point on the plane, P. And then that point on the plane has this vector right here, PQ. Right? And then this line right here is perpendicular to that one. Okay, so what's the distance? The distance of Q to the plane is just the length, right? It's the component of PQ in the direction of N. So the distance D from Q to the plane is, well, it's the length of vector, it's the length of the projection onto the normal vector N of PQ. Right, and what's that equal to? That's equal to PQ dot N over N. Right, the projection itself was PQ dot N over N dot N, which is just the length of N squared, times N itself. Right, that's the projection, and we just wanted the length of that. But N, vector N, over the length of vector N is just 1. Right, so the length just turns out to be this formula here. Right. So, for example, find the distance of from the point 1, 5, 0 to the plane, 3x minus 4y plus 2z equals 6. Okay, notice that when I give you the plane here, okay, well, we've said it before, the normal vector for the plane is n equal to 3 minus 4, 2, just the coefficients of x, y, and z, and then a point on the plane okay, we're not given a point on the plane. Right, but you can always just make one up. Let x and y be 0, and then z is equal to 3. So, like 0, 0, 3. That's fine. That'll work. Or let x and z be equal to 0, and let y be equal to 3 halves. Or let y and z be 0, and let x equal to 2. Right? Any number of things. Or let x and y be equal to 1. If x and y is equal to 1, you get this. So 2z is equal to 7, so z is 7 halves. So 1, 1, 7 halves. You know, I mean, any x, y, and z you want that satisfies this. So picking x and y to be 0 and then solving for z, that's a great idea. Or, you know, whatever else you would want to do. So that's the point P. And then the vector PQ is equal to 1 minus 0 is 1. 5 minus 0 is 5. 0 minus 3 minus 3. So the distance is equal to PQ dot N over N. So this is 1, 5, negative 3 times n. So that's equal to 3 minus 20. 3 minus 20 minus 6 over, we got there, 9, 16, 4. So minus 26 plus 3. Oops, that's the absolute value of that. Minus 26 plus 3 is minus 23. So 23 over square root 29. All right. So again, the dot product and the cross product are giving us, a lot of cool geometric information that would be, a little bit more tedious to find otherwise. Okay. So that's the end of the lecture on this section.